Welcome back to Axial Deformation Examples. We'll look at one more example, which is a segmented bar where the internal forces are not the same in each segment due to the presence of internal loads. In this problem, we're asked to evaluate internal forces through an axial force diagram. The peak internal stress, and by peak I mean absolute maximum. It doesn't matter if the stress is positive or negative. We want the absolute maximum value, and the total deflection or the deflection at the end of the segments. We're given the elastic modulus is the same for all the bars, 29,000 KSI. We're given areas and lengths of each segment. So let's summarize this information. What we're asked to find here, we're asked to find the internal forces F1, F2, F3. We're asked to find the max of the internal stresses, the max of sigma 1, sigma 2, sigma 3. Recognize that we don't necessarily have to calculate all of them. And we're asked to evaluate the end deflection V sub D, which I might kind of draw on there. The whole bar is going to move to the right some amount, presumably to the right. Considering units, everything is given in kips and inches, so we can work with those units, and those are good units for stresses in English units. Our forces will be in kips, our stresses will be in KSI, and our deflections will be in inches. Okay, so the first step is to draw an axial force diagram. And while we could evaluate this reaction at the right end here, we actually, at the left end here, we actually don't need to. We can simply draw the axial force diagram by working from right to left. So I will go ahead and model that process for you. I'm going to set up my diagram right here. Okay, I'm going to label axial force and my units in kips, and I'm going to start over here at the right end and recognize, recall what we learned, that as we cross an arrow, an internal force, the axial force diagram is going to jump up or jump down. So one of the hardest things to figure out is which way it jumps, but we can figure it out by thinking about it logically from working at this end. At the right end, if we isolate and just consider what's happening in segment 3, the force at the end is pulling on it. That means segment 3 is going to be in tension. So the arrow pointing to the right means that as we work from right to left, we cross the arrow, we must jump up. Okay, so we jump up by 8 kips, move over to point C. Now we cross an arrow pointing to the left. 17 kips, we jump down by 17 kips, and 8 minus 17 gives us a negative 9. This force is going to be positive. Force in segment 2 is going to be negative. That means that segment is in compression. And finally, we cross the 30 kip force pointing to the right, so it's going to jump up by 30. Negative 9 plus 30 gives us a positive gives us a positive 21 kips. Okay, so in summary, F1 equals 21 kips, F2 equals negative 9 kips, F3 equals a positive 8 kips. Now we can proceed to evaluate the stresses, and I recognize that the areas in segment 1 and 2 are the same, so looking at these two forces here, I'm going to only evaluate the larger one. I'm only going to evaluate sigma 1 because I know the stress sigma 1 will be larger than sigma 2. The area of segment 3, 0.3 inches squared, is smaller than segment 1 or 2, so even though the force is smaller, I'm also going to evaluate sigma 3 just to be sure. Okay, so sigma 1 equal to F1 over A1 equals 21 kips divided by 0.5 inches squared. I can do that in my head. That's 42 kips per square inch. Sigma 3 equal to F3 over A3 equals 8 kips divided by 0.3 inches squared. I can pretty much see this is going to be smaller. Plug that in. The number is 26.7 KSI. So sigma 1 is my maximum stress here. It's the larger of the two numbers. Max sigma equals 42 KSI, and that's what we would be looking for in the problem. If that's what you were asked, you would need to clearly identify which one was the max. Okay, finally, evaluating the total deflection, we can add together the deformation in each segment through V sub D equals delta 1 plus delta 2 plus delta 3, where each segment, the deformation is FL over AE, so we have F1 L1 over A1E plus F2 L2 over A2E plus F3 L3 over A3E. Now I recognize here that E is the same for all the bars, so when I do my calculations, I can pull that out. 1 over 29,000 KSI. Okay, F1 L1, 21 kips times 36 inches divided by A1.5 inches squared. F2 was negative, so the internal deformation in segment 2 is going to be negative, which means it's shortening. So minus 9 kips times 50 inches divided also by 0.5 inches squared. And then segment 3, F3, 8 kips times 22 inches divided by 0.3 inches squared. And if we plug all those numbers into our calculator, we get 0.041. What are the units? Our KSI cancels out with kips and inches squared in each of these, so we appropriately find that the units are inches. So this is a small deflection, but part of the reason it's so small is that we know that there's the shortening in segment 2 sort of balances the lengthening in segments 1 and 3. So we expect to get a fairly small number there.